Topic 27, Aromatic Chemistry. 27.2, Arenes, Physical Properties, Naming and Reactivity. So we're going to start with the physical properties of benzene. Now we know benzene is a colourless liquid at room temperature. It boils at 353 Kelvin and freezes at 279 Kelvin. Its boiling point is comparable with that of hexane, which is around about the same at 354 Kelvin. But hexane has a melting point which is much higher than hexane's 178 Kelvin, and we need to look at why that is. So we have hexane here. So this is hexane, it's got 6 carbon atoms. So 1, 2, 3, 4, 5, 6. We're going to go for the skeletal formula here. So this is hexane. And here we have benzene. So both benzene and hexane are very similar sized molecules. The boiling point is more or less the same. Because they have similar sized molecules. Hexane is 354 and benzene is more or less the same, and it is 353. That's not a significant difference there. However, when we look at the melting point, what we find is that hexane is only 178 Kelvin and benzene is much higher than that. So it's got a much higher boiling point. Let's look at why that is. This is because benzene is flat. So you could look at benzene from this angle here. If we have another molecule of benzene like this, and they'd line up like that. But if we look at these molecules side on, like this here, and we can represent a benzene molecule as just a line, because we're looking at side on, what happens is that these molecules can pack together very well in the solid state. However, if we look at hexane, the molecules can't pack together as well. Therefore, there's greater van der Waals between the molecules in benzene compared to between the molecules in hexane. Therefore, benzene has a higher value than hexane. So we've looked there at boiling points and melting points there. So just to clarify, similar boiling point, different melting point. Benzene has a higher than expected melting point because those molecules can pack together quite well, increasing the van der Waals force of attraction between the molecules of benzene. Like other hydrocarbons, benzene is non-polar. And that's because it's got no overall dipole. So each of these carbon atoms here are equivalent. there's no overall dipole. There will of course be a very slight difference in electronegativity between these carbon atoms and hydrogen atoms. However, that effect cancels each other out because this is a symmetrical molecule here. Every CH2 here is equivalent if it was cyclohexane. However, remember we've got cyclohexyl-1,3,5 triene, which is actually benzene. We've got CHs here, and again, this is non-polar. There's no overall dipole. So just like hexane and cyclohexane, benzene and other arenes as well. Remember, an arene is just something which is based on benzene. They do not mix with water. That's because they are non-polar, because they don't have an overall dipole. Remember, something like ethanol has an overall dipole, and in fact ethanol can hydrogen bond, so it actually mixes well with water. Benzene doesn't. Doesn't mix well with water, but it does mix well with other hydrocarbons and other non-polar solvents. That's because it's got no overall dipole, just like those hydrocarbons and non-polar solvents. Okay, so we've looked at physical properties now of arenes. Now we're going to look at naming these. Obviously this one here is benzene. We know that. What we're going to now look at is what we call the derivatives of benzene. A derivative is a structure which is based on benzene. Typically, it has this structure here, but with one of the hydrogens replaced with another group or another atom, or maybe two of the hydrogens replaced by two groups or two atoms, or 3 or 4 or 5 up to 6. So let's look at a very simple derivative of benzene here. So instead of having C6H6, let's replace one of those hydrogens here for another group. So instead of having a 6th hydrogen, let's put on a CH3 group. And remember that a CH3 is what we'll call a methyl group. So this is benzene, and this is a methyl group attached to benzene. Then we'll call this molecule here methyl benzene. And the skeletal formula of that will look like this. So this is methyl benzene. So what we've got here is we've got chlorine, which replaces one of the hydrogens in benzene. If it was a methyl group, it's methyl benzene. If it's chlorine, it's therefore chlorobenzene. There we go. And so on. Sometimes there's more than one group or atom. We'll call these groups of atoms that we add a substituent. A substituent is just something that we add to a molecule. So we've got one methyl substituent on a benzene molecule here to make methyl benzene, and one chloro substituent on this benzene molecule to make chlorobenzene. If we have more than one substituent, we have to number the ring. So I have a chlorine here. Let's make that carbon atom a bit more clearer there. It almost looked like a 5-membered ring there, and a chlorine there. Remember, when we're numbering anything really in organic chemistry, naming them, you always try and give the carbon atoms the lowest possible number. So this is not carbon number 1, because that means that would be 2 and that would be 3. We need to give these groups here the lowest possible numbers. So we number from here or from here. It doesn't matter. This is carbon number 1 and this is carbon number 2. So the name is 1, 2 dash di, because there's 2 chlorines, chlorobenzene. So 1, 2, dichlorobenzene. If we move the position of one of these chlorines here, let's say we put 1 on the first carbon and then 1 on the second, third, fourth carbon here, then this is actually a different structure to this one here. This is 1, 4 dichlorobenzene. Some people do this sort of thing by mistake sometimes. You might draw another structure like this, put a chlorine there, and then another one there. I might try and call that something different, but again, that is just 1, 4 dichlorobenzene. Or I might do this. I think this is a different structure, but of course, this is 1, 2 dichlorobenzene, not anything like 5, 6 dichlorobenzene. So we don't want to see that. Okay, let's have a go. Let's test ourselves by naming these structures. So sometimes you'd be given the actual structure in skeletal formula or displayed formula. Sometimes you might be given the structural formula. Sometimes you might be given the name. If you're given the name, you might have to draw a structure. If you're given the drawing of the structure, you might have to name it. Let's do a few more then. So if we're given the name, ethyl benzene, we know it's going to be based on benzene. It's got an ethyl group. Ethyl is 2 carbons. So C2H5. Sometimes drawn like this. So that's C6H5. That's your benzene ring. Minus your group. C2H5. Alternatively, might be given the structure. So this is a new group here. This is an NO2 group, and an NO2 group is what we call a nitro group. So we call this nitrobenzene. C6H5NO2. What's sometimes a little bit more tricky, if we're given the formula here, notice the brackets. So we've got our benzene structure. We notice it's C6H4 this time, therefore we must have 2 substituents. We can see here we've got the 2 substituents. In this case it's 2 methyl groups. Remember, it's 2 times everything in that brackets. So it's a benzene ring with 2 methyl groups on it. Now, from this structure, there is a number of isomers. You could have 1, 2 dimethyl benzene, but of course we can also have maybe 1, 4 dimethyl benzene. Let's draw those. this is 1,2 dimethylbenzene. And this one is 1,4 dimethylbenzene. Of course, you can get 1,3 dimethylbenzene as well. Which would be like this. Now, I can actually leave that structure like that if I want, because remember, in true skeletal formula, you don't actually have to use the hydrogens here, so I can actually just do that, and we'll have a CH3 here and a CH3 there on the first carbon, and on the third, 1,3 dimethylbenzene. So what we've done so far is we've looked at physical properties, naming, and now we're going to touch on reactivity. So we're going to look at the reactivity of aromatic compounds. So the first thing to remember is that high electron density in the ring of aromatic compounds like benzene. So we did that in 27.1. So if we look at that structure here, we've got a ring of electron density above and below the plane of the molecule. Remember, they are formed from the electrons in the carbon p orbitals, which are delocalized. Now, we have a ring above and below the plane of the molecule, and that's of high electron density. Let's just sketch that out again. I'm just going to focus on the ring this time, rather than the actual structure of benzene itself. So we have a ring of electron density above the plane of the molecule. We have benzene here. Let's just draw benzene as a line. That's benzene. And a ring of electron density below the plane of the molecule as well. So we have high electron density, and that's because of the delocalized bonding. And what that means is, because you've got high electron density, it means that benzene can be attacked by electrophiles. Why? Well, to answer that question, we need to recap what an electrophile is. Remember, an electrophile is something which is electron seeking. So because benzene has high electron density, therefore it can be attacked by something which is electron seeking. So that already gives us a bit of an indication about what type of reactions benzene would undergo. So benzene is attacked by electrophiles. Now that's very different to alkenes. So here's an alkene. Alkenes are also attacked by electrophiles. But the difference here is that when an alkene is attacked by electrophiles, this double bond is lost. So the p orbitals, which overlap on the carbon-carbon double bond here to make a pi bond, is no longer present in the product. There's no pi bond in the product. However, what we'll find out is in 27.3, which is the next subtopic, that when benzene reacts with electrophiles, this electron density, which is spread over the p orbitals, is not lost. So that is a difference between the reaction of benzene with electrophiles and alkenes with electrophiles. We'll find that when alkenes react with electrophiles, these are addition reactions, and that's because no atoms are lost, they're just added. But when we find an electrophile reacts with benzene, the hydrogen atoms come off and are replaced by the electrophile. So they are substituted. So benzene undergoes electrophilic substitution reactions rather than electrophilic addition reactions. So benzene undergoes electrophilic substitution reactions, whereas an alkene undergoes electrophilic addition reactions. So you should now already be able to draw the mechanism for an alkene with an electrophile, for example, bromine, in electrophilic addition reaction. So you know that mechanism. And what we will be learning in this topic in 27.3 is the electrophilic substitution reaction with benzene and an electrophile. So that's a first key difference there, which we'll look at in the next subtopic. The next thing, still to do with this ring here, and the fact that this ring is very stable. So because it's very stable, we need to put energy in to break the ring. So energy needs to be put in to break the ring. We call this the delocalization energy. And this delocalization energy is very high because it's very stable. So the delocalization energy required to break the ring of electron density is high. So what we find is, we find that the ring almost always remains intact in the reactions of Arenes. So the ring is at the start of the reaction and the ring is at the end. And we'll see that in our mechanisms in 27.3. Therefore, the ring often remains intact when Arenes react in electrophilic reactions. So the above 2 points here mean that most reactions of aromatic systems are electrophilic substitution reactions. We'll look closely at that in the next subtopic, which is 27.3.